Hola chicos y chicas, soy Nicolás y vamos a hacer una revista de capítulo 5, especialidad sobre sumaciones de Riemann. No, I'm not going to talk in Spanish. So I wanted to, if you didn't understand that, I'm going to be doing a review of chapter 5. I'm going to start with 5.1 and then just kind of go through and I'm going to talk about Ramon Sums for the most part because I think that is where a lot of the confusion is. So 5.1 is dealing with antiderivatives, and I'm going to go through this section pretty quick because I think it's fairly intuitive. The idea is you're just undoing the derivative. That's really pretty much it. For example, if I have f prime of x is equal to 4x plus 7, and I want to find what f of x is, our original function, then it should be relatively obvious that that's 2x squared plus 7x plus c, where c is the ubiquitous constant. And if it's not clear why you add c, think of it like this. If I've got this function here, which is really a parabola, and it goes something like this, maybe, I know it opens up or things like that, but so it does that. Now, I know that this function gives a slope, and I also know that if I shift this function up or down, maybe if I shift it down here by subtracting some constant, its slope, in other words, its derivative, won't change. So adding or subtracting a constant won't affect the derivative, so therefore, to find the what we call the most general antiderivative, we add a plus c at the end. Another way of thinking about this is if I were to check 2x squared plus 7x plus c, and I were to differentiate it, and c is a constant, by the power rule, get 4x plus 7, and then my c goes to 0. The derivative of a constant is 0 because its slope never changes. Now, say, for example, I gave you some sort of initial condition, so to say. So let's say I had f prime of x being equal to 5x to the 4th minus 3x squared plus 4, and I know that f of negative 1 is equal to 2. The point of this initial condition is to find that constant, what c is, because if you know any number at all of the original function, you can just plug that number in and solve for c. So the most general antiderivative of this function here is going to be x to the 5th minus x cubed plus 4x. Now I know that f of negative 1 is equal to 2, so 2 is, I'll write it out, negative 1 to the 5th minus negative 1 cubed plus 4 times negative 1, which is negative 1 minus a negative 1, so plus 1, minus 4, which those cancel, we get a minus 4. So since we have restricted our function by this initial value or initial condition, as you will hear it called in a textbook, the only function that satisfies both this and this is the following. F of x is equal to x to the 5th minus x cubed. Oh, I should have had a c here, whoopsies. Plus 4x minus 4. And that is the only answer in that particular case when we have this initial condition. That honestly takes care of 5.1. That really is about all I want to talk about 5.1. Now, 5.2 is Ramon. It's really Ramon Sums. So Ramon Sums are basically how we define an integral. And I'm sure most of you watching, at least in my class, know the basic idea of a Ramon sum. I'm not going to elaborate on that so much, you know, we got a function, and we if this, oops, I'm trying to try it with this line tool here, the straight line tool. And let's say we want to estimate its area from A to B. This is a function f. It's positive and increasing. Then we can just take rectangles. I'm not sure how much I like this. And normally we would have them evenly spaced, but I'm not going to put all of, and they would actually be rectangles. They don't look so good right now. They'd be evenly spaced, and oh, whoa. Be evenly spaced, and now notice here, what we're doing is, you see how these rectangles all touch on the left. They touch the function on the left side. Now I just chose the left side. Now, of course, we could have done the right side. If I redraw it here, if I've got something like that, and the same function a to b, function f, I could do it like this. So now here the right's touching, the right's touching, the right's touching, and I think you get the idea. And there is, say in this picture here, there's n rectangles. Then as the number of rectangles approaches infinity, we approach the area, and if we just take the limit as the number of rectangles approaches infinity, we get the exact area. Now, what this is saying is that, so we have a starting point at A, and we end at a B, an x value of B, and there's n of these rectangles, and they're all equally spaced. So the distance between each rectangle, delta x, is b minus a over n. That should be relatively intuitive. It's just this distance here divided by how many there are. And that's the distance between each one if they're evenly spaced. Now, in the textbook, you may have seen that integral a to b of f of x dx is equal to the limit as n increases without bounds of the summation from I is equal to 1 to n of f of x sub I times delta x. Now, this is a slightly compact way of writing it, in that we can do better than this. So first of all, let me just explain some of the variables here. I is the indexing variable. So in other words, I tells you what number rectangle you are on. In other words, see, like here, this is the first rectangle, so I is equal to 1. This is the second rectangle, I is equal to 2. This is the third rectangle, I is equal to 3. So there's a difference between I and n. I tells you the number of the rectangle you're on, n tells you how many rectangles there are in total. So x sub I is the ith rectangle, and x sub I is a plus I delta x. And the way I've always thought about this is that it's like an arithmetic series, right?